Today we will talk about the drilling degrees of freedom in membrane elements. Now remember that when we draw the kinematic relationships, in other words, the relationship between the nodal displacements and the strains, we didn't use the rotational in the out of plane direction, in the z direction of the member. So that's why our classical membrane elements didn't have any drilling degrees of freedom. Now the degrees of freedom interpolation is first proposed by Ullmann. Interpolation for drilling degrees of freedom, and we will follow this interpolation function. So as a starting point, we take an edge of a member. Now in this edge I have a rotation here and another rotation here. Let's call it omega j and omega I. So in this interpolation, it is assumed that drilling degrees of freedom are associated with parabolic displacement at element edges. So here we are assuming a parabolic displacement at the element edge, and at the middle we have the delta m. And let's put a coordinate axis here, that the local x of the element, local y, and here we have the displacement in x direction. V will be the displacement in y direction, and this displacement delta m will be at the element, middle of the element edge. So we say that the drilling degrees of freedom at nodes I and j produce edge normal displacement delta m, and this delta m is equal to, when we assume a parabola, that's the displacement L over L and the difference between the rotations. Okay. Now if I want to write these displacements with respect to the coordinate axis that I defined, so remember that that's delta m, so we have an angle with the local x. Let's call this angle as alpha. So I'll just exaggerate and draw delta m here. So this distance, or this translation, this is alpha, will be equal to alpha m times cosine alpha, and this distance will be delta m times sine alpha. So I can write the displacement, mid-edge displacement components as follows. That will be equal to L over 8 rotation j minus rotation I multiplied with cosine alpha and sine alpha. Okay, now if I introduce, now let's introduce a coordinate axis. Let's say that that's S. Now introducing a parabolic shape function. For the edge displacement delta, so at the ends it should be equal to 0, at the middle it should be equal to L over 8 multiplied with these additional parameters. So my edge displacement interpolation will be equal to L minus S multiplied by S divided by 2L omega j minus omega I multiplied with cosine alpha and sine alpha. Okay, so this is the edge displacement due to nodal rotations only. So we may have some translations in the u directions and in the v directions. So let's add that and have a complete displacement field definition for a single edge. Okay, so introducing a linear shape function for translational nodal degrees of freedom. And combining it with the edge displacements. So with delta yields so I had the displacement field as follows: uv is equal to L minus S divided by L uv plus S over L u and v plus the mid-edge parabolic displacement due to nodal rotations, L minus S multiplied by S divided by 2L omega j minus omega I cosine alpha and sine alpha. So this interpolation was for a single edge, and this is a linear interpolation for nodal translation, and we have a parabolic interpolation for nodal rotation, or let's call it drilling rotation. Okay, now this is for a single edge. Now let's try to write the same thing for a quadrilateral element. Okay, so for a quadrilateral element, how can I extend this interpolation? Let's see that. Let me rewrite it. quadrilateral element. I will just write it as follows. So this is the element that I have. This is node 1, node 2, node 3 and node 4. And I will name the mid edges as follows: node 5, node 6, node 7 and node 8. Now, so I will use this following notation. For I is equal to 5, 6, 7 and 8. I have a j parameter and k parameter. J will be equal to 1, 2, 3 and 4. 5, sorry, this should be 2, 3, 4 and 1. So what I did here is I just relate the mid edge with the edge 1, 2. Okay, that's I represents your points at the mid edge locations, and JK couple will represent the edges defined by the start node and the end node. So this is the start node for the edge, this is the end node for the edge, and we can just say that this is edge 1, edge 2, edge 3 and edge 4. Okay, now let's come back here. So we said that we have a linear interpolation for nodal translations. Okay, so we know how to write it for a quadrilateral element. So this is U, this is V. That's equal to, so N is equal to 1 to 4. This part is very similar to the bilinear element Ni multiplied by nodal displacement in x direction, nodal displacement in the v direction. So this part is the linear interpolations for the nodal translations. Now I have to rewrite that for each edge. Okay, so plus I have I is equal to 5 to 8. Now I will be using the quadratic shape functions. We will plot it later on, but the quadratic shape functions from 5 to 8 will give you a interpolation function shape like that. So this distance will be equal to 1 and the rest will be equal to 0. So the sixth quadrilateral shape function will give you that this is equal to 1, the rest is equal to 0 and so on. Okay, so I will just use NS for that. It's called also the serendipity shape functions. I have to correct one thing here, that these shouldn't be i's, they should be n's. Okay, sorry, this is n and n and n. Now in this case this is I, so I'm using the 5th, 7th, 6th, 7th and 8th of the quadratic shape functions, and these shape functions will give me 1 at every mid node. Okay, and it's like this is the 2D version of it, and this is the same shape function in this for this surface. So ns1 multiplied by, so we have L over 8 here, because at the middle the translation should be equal to L over 8 multiplied by the differences of rotations multiplied by cosine theta, cosine alpha and sine alpha. So mid h is equal to 1, L over 8 multiplied by, in this interpolation, let's take a look, end node minus start node. So I should have the rotation at the end node, theta k, minus the rotation at the start node, theta j, multiplied by the outward unit normal of this edge, and I just show it as cosine alpha jk and sine alpha jk. Now for this element, this is the new interpolation function. This part is for the translation of degrees of freedom, is exactly the same as the bilinear membrane element. Now we have the additional displacement field interpolation in terms of the nodal rotations. Okay, so this is our nodal rotation. Of course, our coordinate translation is the same. R is equal to 1 to 4 ni xi. So the coordinate translation is linear, but the displacement interpolation is linear plus some quadratic terms here. Now let's try to figure out the strain displacement relationship for this new displacement field. So epsilon xx is equal to del u over del x. So I will just write it for the second part of it, because as I said, this part is exactly the same as the bilinear element. Okay, so I'll just put some dots for the translation part, and plus I have del ns 5 divided by del x multiplied by L12. So I should write jk here also. Length of the h1 divided by 8 multiplied by theta 2 minus theta 1, difference of rotations along h1 at the ends of h1, and multiplied by cosine alpha 1 2, and this one to represent length of h1 and the cosine of the outward unit normal of h1. Plus, we'll switch to second edge, del ns 6 divided by del x plus, not plus, multiplied by L23 divided by 8. I have theta 3 minus theta 2 cosine alpha 23. This is for the second edge. Now the third edge, del ns 7 over del x multiplied by L34 divided by 8, theta 4 minus theta 3 multiplied by cosine alpha 34, and finally the fourth edge, del ns 8 divided by del x multiplied by L41 divided by 8, theta 1 minus theta 4 cosine alpha 14. Okay, and this is also for the edge 4. Now this is the strain interpolation now, but I don't like the structure of this part, because in order for me to generate the B matrix, I need the coefficients in front of theta 1, theta 2, theta 3, and theta 4. Okay, so rewriting expression for epsilon xx, I have the following. del u over del x is equal to, again we have the linear terms, plus, so in front of theta 1 I have this coefficient, so let's write it first, del ns 8 over del x multiplied by, now I will just write, instead of 4 1 I'll just write the name of the edge, L4 divided by 8 multiplied by cosine alpha 4. Then I have this parameter here in front of theta 1, it's minus, and this one minus del ns 5 divided by del x L1 over 8 multiplied by cosine alpha 1, and this is the coefficient in front of theta 1 in the strain displacement matrix. Then I'll continue. Del ns 5, now I'm looking at theta 2 over del x multiplied by L1 over 8 cosine alpha 1 minus, I have minus del ns 6 times L2 over 8 cosine alpha 2 theta 2. Then if you continue, you'll see that this is ns6 over del x multiplied by L2 over 8 cosine alpha 1 x minus del ns7 over del x times L3 over 8 times cosine alpha 3 theta 3, and our final expression here is del ns7 over del x multiplied by L3 over 8 cosine alpha 3 minus del ns8 over del x times L4 over 8 cosine alpha 4 multiplied by theta 4. So this is the expression for del u over del x. Now if I write an expression for an equation for del v over del y, the only thing that will change in this equation is this replace, I can just write del over del x with del over del y, right? And replace cosine alpha with sine alpha. So this part remains the same, this ordering remains the same. So the only thing that I will change is, instead of del over del x, I'll take del over del y, take the derivative of this quadratic shape function with respect to y, and instead of cosine, use sine. And for the shear strain, you have del u over del y plus del v over del x. So the only thing again you'll change is these two values. So with this approach, you'll obtain your B matrix. In that case, let's write it this way. We obtain the B matrix that will relate B times U. U will be, let's write it like that. We have the translation of the first node and the drilling rotation of the second node. Translation of the second, drilling of the second, and V4 and theta 4. That's our nodal displacement vector. Now we have 12 degrees of freedom, and B matrix will be 3 by 12. And again, the stiffness matrix, you can repeat the same procedure. Start from the energy functional, take the first derivative, and in that case K can be evaluated as integral B transpose E times B, and integrated times thickness dA. And this expression will give you the stiffness matrix. And in this stiffness matrix, we will have the coefficients of the coefficients for the drilling degrees of freedom right here, and these drilling degrees of freedom, these rotations, depends on the mid-edge displacement. They are calculated from the mid-edge displacement. Now if you take a look at the expression for the theta 1, for example, it's the difference between the mid-edge displacement of edge 4 and the mid-edge displacement of edge 1. In other words, this is, if let's say that it moves this much and it moves this much, you have a interpolation like that. So you calculate the differences of these two and obtain your rotation. In other words, here the rotations are calculated with respect to the displacements of the neighboring mid-edges. That's the interpolation here. Okay. Now we can calculate the stiffness matrix, but when we do that, we realize that this element is not mechanism free. So what does that mean? Let's take this element again. I have a square element. Let's take a look at that. The element deforms in such a way that all rotations are equal to each other. Okay, let's consider this deformed shape. So when that's the case, these are the mid edges. This is what we observe. So I'm just rotating the nodes. They all have the same rotations. So the deformed shape that I see for this edge is as follows. For this one is as follows. This one. So when all the rotations are equal to each other, so these are the rotations, right? All mid-edge translations are equal to 0. So what does that mean? For this given deformed shape, there's no stiffness in the element. In other words, the element cannot resist, the stiffness matrix that we generate cannot provide any resistance for this given deformed configuration. So which indicates that we have a singularity in our element stiffness matrix. If you calculate your element stiffness matrix this way, it's very probable that you may not obtain any solution. Especially, let's say that you are solving a problem with a single element, you end up with a singular matrix, okay? Because you don't have a stiffness for this type of behavior. And this is called the mechanism in your element. So this mechanism causes instability. Okay. So this is called, sometimes the mechanism is called is for the element you can find in the literature, they are called as zero energy or spurious modes. Sometimes you can find it as the hourglass mode also. So these are the way this problem is referred in the literature. Okay, so what to do? I mean, we did a very nice interpolation. It looks like it was working. Now we have a mechanism in the element. So you will see that there are several remedies for that, but I'll just go over the simplest one. So I know that for this given deformed shape, we don't have any stiffness. So I will just put a very small stiffness for this type of behavior, all right? And it should be small so that it will not influence the problem, and the energy that it introduces to the whole system should be equal to 0. So this is one of the approaches. So we can say that in order to eliminate zero energy mode for this element, a small stiffness, a small resistance can be added to the drilling degrees of freedom to prevent instability. And the proposed additional stiffness has the following form. So I'll just call it K theta is equal to 1/36, a coefficient and alpha, elastic modulus times T to the power n, multiplied by the area of the element, and the matrix will have the following form: 1.75 minus 0.75 minus 0.25 and if you take the determinant of this matrix, you will see that it's equal to 0. And this is a small number. You can put an extremely small number, provided that it doesn't cause any numerical problems in your solution algorithm. So that's an easy and simple way, effective way of doing it. We just provide some stiffness, but there should be a better method. Aren't there any better methods? Yes, there are. Now, the plane stress problem that includes drilling rotations. Remember that the plane stress problem that we defined here didn't have any drilling degrees of freedom. They all depend on the translations in the U and V direction. But you can do it a different way of defining it, and it was done by Reisner in 1960s and extended to the finite element method by Hughes and Breze. So I will put the paper of Hughes and Breze. You can just take a look at it. It's not easy to understand, but it proposes a different way of stabilizing that element. So that's mainly it about this element. So let's take a look at how we can implement this. Okay, now let's take a look at the implementation of the membrane element with drilling degrees of freedom. Now we start with defining the shape functions for the 4-node isoparametric element. So this is again the bilinear interpolation. Now, different from the previous interpolation, I'm directly calculating the d over dx. Now this is Jacobian 1 multiplied by this one, and Jacobian 1 2 multiplied by this one. So with these matrices, I'm directly obtaining the derivatives with respect to x and with respect to y. Now in this element, we said that we are using the quadratic shape functions, but not all of it, just from 5 to 8, but I just write the whole quadratic shape functions here and their derivatives as follows. Now let's plot these quadratic shape functions. So this is the first one. In other words, it's the plot of this, the first equation in the natural coordinate system. So as you see, it's equal to 1 at one of the nodes. So the rest, the mid nodes and the other nodes, they are all equal to 0. Okay, that's the plot of the first quadratic shape function. But what we are mainly interested is the plot of the fifth shape function. So as you see at the middle, at psi is equal to 0, that value is equal to 1, and elsewhere it's equal to 0. Okay, and this will be our mid-edge interpolation that we are going to use. And if you do the same thing for the 6, you will see that it will have the shape like that. So these are the quadratic shape functions. And again, for simplicity, I'm just calculating their derivatives with respect to x and y in here. Now, in our displacement interpolation, we will need the edge lengths and the unit normals. So you can just calculate the edge lengths as follows. So these cyclic indices represents the edge definitions. So you can calculate the length and you can calculate the outward unit normal. This is basically equal to delta y over L, and this is equal to minus delta x over L. But if you recall the displacement interpolation, we are multiplying the cosine with the length of the member. So actually we are not directly using these values, but we are using the normal times the length parameter. And if you multiply the length with the unit normal, you will see that their multiplication will be equal to delta y, and also this one will be equal to minus delta x. So here I'm using this algorithm to calculate the normal or the angle cosine of or sine of the angle times the length. Here there's nothing special here, the Gauss points, locations and their rate functions. Again, as we said, our displacement interpolation was as follows. We said that x is equal to I is equal to 1 to 4 ni xi, and that's why we calculate the Jacobian matrix only by using the derivatives of the bilinear shape function. Plane stress case, there is no change in the constitutive relationship. Now let's take a look at the strain displacement matrix. As we discuss this first part, this part is exactly the same as the bilinear element. There's no change in that. But this part is our new interpolations for the rotations, effect of rotations on the strains. Actually, this is what we calculate. Now the axial strain is this one. So I have a cyclic again indices here, 8, 5, 6, 7 represent these indices, all right? And 4, 1, 2, 3 represents these indices. 5, 6, 7, 8 are these ones, 5, 6, 7, 8. And of course our main index is I, 1, 2, 3, 4, okay? So if you take a look at this one, I'm taking dns, dx, and using the first index of ms. So it's this part, this one, multiplied with the cosine of the normal with the length, it's this one. This shows that it's cosine, and here I'm using this in this now. 4, 1, 2, 3 divided by 8 will give me this coefficient, and this one will give me that coefficient. So m changes, you know, it goes like 3, 6, 9, 8, 12. So at every rotations I'm just putting the corresponding coefficients. Okay, now we said that the del v over del y, replace del over del x with del over del y. So as you see, I'm just replacing it. Instead of the x, I'm using the derivative with respect to y, and replace cosine alpha with sine alpha. So instead of using the first coefficient of that output of that normal length subwritten, I'm using the second coefficient, and this is the shear strain interpolation. So this way I'm generating the B matrix for a given Gauss point. Now we said that we have to add some additional stiffness to the drilling degrees of freedom, so that we will end up with a singular stiffness matrix, and this was the approach. So here I'm just using the elastic modulus and volume. I'm not using T to the n because I'm just dividing with a very large number, 150,000. So I'm not really modifying this coefficient. I'm just putting a very small number in there. And this is I'm just writing the stiffness matrix as follows. There's nothing special in the element stiffness matrix calculation, so we are using 2x2 integration for this element. You can try 3x3, you get the same results, but I do 2x2 here. Calculate the B matrix, B transpose E times B, and this is the requirement for the numerical integration. So the rest of the equations are the same, but this times at every node we have 3 degrees of freedoms. In the bilinear or in the incompatible elements we were having 2 degrees of freedom per node. So only difference is here we got 3 degrees of freedom. Here and then the global stiffness matrix, I'm assembling the stiffness matrix of every element. The stiffness matrices will be 12 by 12, and we have again the displacement calculations. Now let's take a look at the results. Oh, before that, of course, we will have to discuss the element nodal force computation. Again, there's nothing special about it. The same approach with the bilinear element. K times U will give me the nodal forces, and at every point I'm calculating stresses as displacements times U will give me the strains, multiplied with the constitutive relationship will give me the stresses. Now the example problem, again I'm solving the same problem. Let's remember the results. So the tip displacement is equal to 0.00237 meters. This is without shear deformation, and with the shear deformation it's equal to 0.0024. This is with shear. Remember that this is for the obtained with the beam theory. Okay, now the stresses, the axial stress here is 3333.3 kilopascal, and the shear stress, if I use shear area, is equal to 100 kPa. But if you don't use, if you calculate the shear by just dividing the shear force with the area, you get 83.3 kPa. Okay, so these are the analytical results, and remember that these analytical results were obtained from the beam theory. Now we are solving the same problem with the finite element, but I have the Poisson ratio here, which may slightly change the results. Okay, now first let's take a look at the single element solution. Now the way I'm defining is as follows. So remember that that's a fixed cantilever. So I'm just fixing the translations as well as the rotations. Okay, I'm also fixing the drilling rotations. And with that, when we look at the results, we get significantly small tip displacement. Okay, so we did all these things, but the result is significantly small. The reason is this: fixing the drilling degrees of freedoms didn't work for us. Why? Because our discretization is as follows, right? So this is node 1, node 2, node 3, and node 4. So when I fix the drilling rotations, these 2 degrees of freedom, I'm not only fixing the rotations, but I'm saying that these mid-edge displacements are also equal to 0. So remember that this is what we are doing. When you fix the drilling degrees of freedom, you are saying that mid-edge displacements must be equal to 0. So we are saying that this element can only bend maybe in this form. So because of this reason, this midpoint is not free and it's at 2 meters, we see a very small displacement. Now in the second case, the same problem, but now I'm just letting the rotations be free, okay, at the supports. They are not restrained. And what about the displacements in that case? I didn't obtain any instability, and now the displacements are equal to 0.0017, which is acceptable for a single element solution. What about the stresses? Of course, the element is in equilibrium. There is no change in the nodal forces, but the stresses, we were expecting to get 333 for the axial displacements, but these displacements are almost half of it. We see stresses in the other direction. This is because of the Poisson effect, and the shear stresses are as follows. These are the shear stresses. We were expecting to get 100, but these are around 83. So I should increase the number of elements that I use to obtain a better solution. Again, I'm discretizing the structure by using 5 elements, and when I look at the results, the displacements are in a much better shape. So it's like minus 0.00228. So we were expecting 0.0024 or 23.237. So it's very close, and this also shows that by defining the drilling degrees of freedom, we are actually introducing a higher order shape functions to that member by using the mid-edge displacement, and that also eliminated the shear locking or the membrane locking that we observed in the bilinear element. What about the stresses? Now stresses are not exactly the same, are not what we expect. This is 3000, so there are 10% error in the stresses, and the shear stresses that we obtain is very close to the one without any shear area correction. So in order to see the shear variation within the depth of the member, remember that we expect a variation like that. I should mesh it with more elements so that I can see this shear variation. So if I use a single element with respect to the depth of the member, I see a constant shear strain not corrected with the area. And we can say that we have the drilling degrees of freedoms in this element that eliminates the locking and also gives good results, very close to the results with the incompatible membrane element.